Let's talk now about locks in xv6. In particular, we're going to look at the IDE device driver. So what we have are two routines. IDE read-write, and that issues a block request. And then we also have IDE interrupt, which completes a block request. And they both share a linked list of blocks. And so what happens is IDE read-write inserts into the list at the head, and IDE interrupt removes from the list. And so the problem that could occur is that they both are trying to manipulate the list at the same time. And so therefore we have a lock, which controls access to this list. So the lock, let's just look at the implementation of this lock, okay? It's a structure that contains a single value saying whether it's locked or not. And let's look at what acquire does. So this is how it could be written, acquire. It's not written, and we'll see why in a moment. So we go through, we get our lock LK, we have our for loop, and basically we just keep checking, is it locked or not? Okay. If the locked field is false, then we go ahead and acquire the lock and then break. The problem is we have a race condition, okay, between lines A and B. So what happens is if two processors come in and they both check to see whether the lock is locked, so the lock is not held by anybody at this point. They both come in, they both find out that it's not locked, and then both set the lock to 1. And so both of them think that they acquired the lock, and yet we don't have mutual exclusion between the two. They're both running. So we're not implemented this way, okay? Because these two lines are not atomic, right? This line and this line are separate, and so we can go on from this line and get to that next line without any guarantee of atomicity. So the problem here is we've got two parts. We've got the testing part, and then we've got a setting part. So it'd be nice if we had really some single instruction that was a test and set. Many processors, architectures do have a test and set instruction. On x86, we do something different. So on x86, we have an atomic exchange operation. So the exchange, basically what we do is we move a value into a register, and then we go ahead and exchange the EAX register with an address in memory. This exchange operation is an atomic operation. So what really happens, right? Basically in hardware, what's going on is this. In hardware, the address gets locked so that no other processors can access it, and then reads from the address, and then writes the value from the register into the address, and then writes a temporary value into the register, and then unlocks the address. So this all happens atomically. So if the value in the address was 1, then when we return from here, the value in the address will still be 1, and the value in the register will be 1. If, on the other hand, the value at the address was 0, then when we are done with the exchange operation, the value of the address will be 1, and the value of EAX will be 0. So that allows us to somehow do both of these at once. So what we can change this to is so this, I'm going to assume here that the exchange is going to turn into this single instruction. All right. So we're going to take, this is the address, and this is our value. So if locked currently is 1, then when we go ahead and do this exchange, the result, we're going to be the result of what was there, and that's going to be 1. And so the if statement won't be true. So it's going to continue cycling until the locked was 0. And if the locked was 0, then the result of this exchange is going to be 0. When we not it, it's going to be 1, and we'll break out. And we're guaranteed that if two processors are trying to go to this simultaneously and locked is 0, only one of them will succeed in the exchange. That is, one of them will get back a 0, and the other one will get back a 1, because this one will write first, put a 1 in there, and then the second will return a 1. Okay. By the way, this kind of a lock is called a spin lock, because of the fact that our CPU is just spinning in our for loop. The other thing we want to do for these locks is ensure that not only do other processors not execute code while we're in our critical section, but also that no interrupt routines also try and interrupt our critical section. And so therefore, in acquire, the xv6 actually disables interrupt, and then in the release, it re-enables interrupt.